By now in this season, you have met a machine that paints a photo from a sentence, a different machine that animates a clip, another that sings a song, another that sculpts a three-dimensional shape you can turn around, and it feels like a zoo. A separate miracle for every medium, each its own strange box of math, learned from scratch with nothing to do with the others. That is the natural impression, and it is almost completely wrong. Here is the claim this whole episode is going to earn. It is not a zoo. It is basically one animal, wearing 4 different coats. The image model, the video model, the music model, the 3D model underneath, they run the same engine. And not a new engine you have to learn. It is an engine you already met back in the very first season, inside the thing that finishes your sentences. Once you see that one skeleton, every medium in this season stops being a separate mystery and becomes a variation on a single theme. So let us go find the one animal hiding inside the zoo. 20 seconds of memory first, because everything rests on it. In the first season, we took apart the engine inside a chatbot. A sentence gets chopped into tokens. Each token becomes a vector, a point in a high-dimensional space. And then the key move, attention. Every token looks at every other token and asks one question: how relevant are you to me? The words with high relevance get mixed in strongly, the irrelevant ones barely at all, and each token updates its own meaning in light of the whole sentence. Stack that operation many times and you get a transformer, the thing that predicts the next word. That is the entire recap, and I am not going to rederive a word of it. Here is the only sentence you need to carry forward. Attention is just every element of a sequence asking every other element how relevant are you, and mixing accordingly. Read that again and notice what it never once mentions. It never says the elements have to be words. That indifference, attention not caring what the tokens actually are, is the whole story of this episode. So let us walk that indifference straight into the image model. Remember from the painting episode what an image generator actually is underneath. It is a denoiser, a network that, given a field of static and a sense of how noisy it is, predicts the nudge toward a clean picture, and you take that step many times until order appears. The question this episode cares about is not the diffusion loop. It is a narrower one. What kind of network sits inside that loop doing the predicting? For the first few years, the answer was a UNet, a convolutional network built for vision that scans an image with small sliding windows, good at local texture, but with a built-in assumption that nearby pixels matter most and distant ones much less. That assumption helps when data is scarce, but it caps how well the network can tie the whole picture together. Then in late 2022, 2 researchers, Peebles and Zai, tried something that sounds almost lazy. They threw the vision-specific UNet out and dropped in a plain transformer instead. The same attention machinery from the chatbot, now denoising an image. They called it the diffusion transformer, DiT, and the reason it mattered was not just that it worked. It is what happened when they made it bigger. Here is the property that turned a clever swap into a landslide. When they scaled the transformer up, more layers, wider layers, more tokens to chew on, the images got better in a clean, predictable line. More compute, lower error every time, no wall. If that sounds familiar, it should. It is exactly the behavior that made language models explode. You pour in more scale, you reliably get a better model. The UNet never gave you that clean a curve. Their largest version set a new best score on a standard image benchmark at the time. And I want to be careful here, because one number on one benchmark on one date does not crown a champion forever, and the score they used is a flawed yardstick we will pick apart in a later episode. So do not read it as transformers are objectively best at everything. Read it as the thing that actually mattered. The denoiser had stopped being a special-purpose vision gadget and become a general sequence model, one that scales like a language model does. That is the door this whole episode walks through. Once your image network is just a sequence model, anything you can turn into a sequence can ride the very same machine. But wait, A sentence is obviously a sequence, words in a row. A picture is a flat grid. How do you feed a grid to a machine built for a line of tokens? With one move so simple it feels like cheating. You chop the picture into a grid of little square patches, and you read them off in order, top left to bottom right, like words across a page. Each patch becomes one token. You tag it with where it sat so the model knows the layout, and now your image is just a short sequence of patch tokens. That is it. Here is the one sentence to keep. A patch is to an image what a word is to a sentence. Once a picture is a sequence of patch tokens, the chatbot's machinery transfers wholesale. Attention lets every patch ask every other patch, how relevant are you? The top of someone's head talking to the bottom of their chin, the left edge of the sky talking to the right, so the whole image stays coherent. One honest detail so you are not misled. The model usually does not chop the raw pixels. The picture is first squeezed into a smaller, compressed version by the encoder you met earlier, and the patches are cut from that. Same idea, just on the compressed image. Patches in, attention over patches, picture out. Now the question that should be bugging you. The image patches can talk to each other, fine. But how does the word corgi end up in the right pixels? The prompt is over here, the picture is over there. How do they meet? And the answer is the most satisfying unification in this whole season, because it is not a new invention at all. It is the exact same attention operation you already know, used with a tiny twist. In the chatbot, attention was a sequence talking to itself, every word asking every other word, how relevant are you? Self-attention. Now take two different sequences. The image patches on one side, the prompt's words on the other. Let every image patch ask the question, but ask it of the words. How relevant is each word to me? The patch that will become the dog reaches out and finds corgi most relevant, drinks in its meaning, and shapes itself accordingly. We call this cross-attention, but do not let the new name fool you. It is the identical machinery. Same questions, same weighted mixing. The only difference is who is asking whom. In self-attention, a sequence questions itself. In cross-attention, one sequence, the image, questions another, the text. That is the entire trick by which a sentence steers a picture. Researchers can even watch it happen, lighting up which patches are paying attention to corgi, and the dog-shaped region lights up. One precise point here, because it is the single easiest thing to get wrong, and getting it right is what separates a real understanding from a vague one. Not every kind of steering needs cross-attention. If all you are telling the model is a single simple label, say, this should be a picture of a dog, that is one little vector, and you do not need a full conversation to deliver it. You can just use it to nudge the network's internal dials, a lightweight tweak. But a real text prompt is not one label. It is a whole sequence of words with structure and relationships, a corgi wearing a spacesuit on the moon. To deliver something that rich, you need a sequence talking to a sequence. You need attention, so keep this crisp. A simple label nudges the dials. A text prompt earns full cross-attention. And in 2024 came the upgrade that defines today's best image models. Instead of keeping the text politely off to the side and letting the image consult it, why not pour the image tokens and the text tokens into one single sequence, and run one big attention pass over all of them together? Now it is not just the image asking the text. The text updates in light of the image too. They become equal citizens in one stream. This design, called MM-DiT, is the reason the latest models finally got good at the thing older ones famously botched, spelling actual readable words inside the picture. When the letters are full participants in the attention, the model can keep them straight. Now the payoff. We built this whole machine for images, but look at what it actually requires. A way to turn the data into a sequence of tokens and an attention engine over those tokens. The engine does not care what the tokens are. So here is the recipe for the entire rest of this season. Keep the attention engine exactly as it is. Change only one thing: how you chop the data into tokens. Watch. For video, you do not treat it as a stack of separate pictures. You take a chunk of space and time together, a little cube, a patch that has width, height, and a slice of duration, and that cube becomes a token. Run attention over those, and now patches can attend across time. The cup at 2 seconds checking in with the cup at 0 seconds, which is exactly how a thing stays the same thing while it moves. For sound, you chop the audio into little coded chips, audio tokens, and either predict them one after another like words, or denoise a grid of them like patches. Either way, a sequence plus attention. For 3D, you carve space into a sparse grid of cells and let the occupied cells be your tokens. Same engine, 3 dimensions, one skeleton. Image, video, audio, 3D, the only thing that changed from medium to medium is what you decided a token is. Learn the engine once, and every zoom in for the rest of this season is just a new tokenizer bolted onto the front of a machine you already understand. Step back and ask the deeper why. Of all the network designs in history, why did this one eat every medium? 3 reasons, and they are the very same 3 that made it win language, which is the real tell that something fundamental is going on. First, reach. A convolution only ever sees a small neighborhood, and the old step-by-step networks pass information along and forget it as they go. Attention lets any element directly touch any other in a single hop. That is what keeps a face symmetric across a whole image, a melody's theme returning 30 seconds later, an object the same object across 100 frames. Long-range coherence is just attention reaching far. Second, speed at scale. Attention chews the whole sequence at once instead of crawling through it one element at a time, which means it saturates modern hardware, which means you can train it on staggering amounts of data. Generation is hungry for scale, and this is the architecture built to be fed. Third and most subtle, it assumes almost nothing. A vision-specific network has strong opinions baked in about how images work. A transformer walks in nearly blank and learns the right structure from the data itself. And here is the honest condition on all of this, not a footnote, the actual rule. Transformers do not win everywhere by magic. They win when data is abundant. When data is scarce, those baked-in assumptions of the older networks genuinely help. But generation lives in the land of oceans of data, and in that land, the blank, scalable, far-reaching engine wins. The same bet that paid off for language, paying off again for pixels and sound. Now the honesty, because one engine for everything is a slogan and slogans round off the truth. 5 things fast and plain. 1. It is not literally one network you can go download and point at anything. The shared part is the attention backbone. The front end, the thing that turns video or sound or 3D into tokens, is bespoke and genuinely hard to build, a different specialist for each medium. Same skeleton, different mouth. 2. The transformer replaced the denoiser inside the loop, but the loop itself, the diffusion or flow process and the compressor that shrinks the data first, those are still very much there. Attention is the backbone, not the whole body, and diffusion did not go away. 3. There is a real design choice we glossed. Simple labels nudge the dials, rich prompts earn full attention, and there is engineering in choosing well. Do not flatten it to everything uses cross-attention. 4. And this one bites. Attention's cost grows with the square of the number of tokens. Double the tokens, quadruple the work. A long, high-resolution video is a monstrous pile of tokens, which is exactly why video is short and expensive, and why a small army of researchers is busy making attention cheaper. It scales beautifully at a known and sometimes brutal price. And 5. For the closed, frontier products, we are often reading the tea leaves. The exact recipe inside the biggest commercial models is usually not published, so when anyone tells you precisely how the newest one works, treat it as an informed guess unless a real paper backs it. Those caveats do not weaken the idea. They sharpen it. So here is the shape of the whole thing in one breath. It looked like a zoo, a different miracle for every medium. It is not. It is one engine, the attention engine you met in Season 1 finishing your sentences, with the data swapped underneath it. The denoiser inside an image model stopped being a vision specialist and became that same general sequence machine. A picture became a short sequence of patch tokens. A patch is to an image what a word is to a sentence. The prompt steers it through cross-attention, which is not a new trick but the very same attention, one sequence questioning another. And then the move that this episode was really about. Keep the engine, change only the tokenizer, and the identical machine paints the next patch, predicts the next slice of spacetime, lays down the next note, fills the next cell of a 3D shape. One mechanism, many fuels. So when the coming episodes go deep on video, on sound, on three-dimensional worlds, you will not be meeting 4 new machines. You will be meeting 4 new tokenizers feeding one engine you already understand. The attention engine that learned to predict the next word turned out to be the universal substrate for making anything at all. Let us go watch it make a world that moves.